Hello, welcome to another lecture on modeling, analysis and estimation of three-phase unbalanced power network. We have been talking about the calculation of impedance matrix in the presence of ground conductor. In the last lecture, we have looked into the process of calculating the impedance matrix in the presence of one ground conductor followed by one example. So, let us today extend this concept and see that if there are in the line more than one ground conductor, so then how do we proceed? So, essentially the idea is basically the same. Idea is basically the same that we consider say three lines. So, this is A dash, B dash, then C dash, and then say that this is U dash and W dash. So, basically, so this is a local ground. We are doing the same thing actually again and again and again and again, local ground, and this is a ground conductor, this is also another ground conductor, and this is phase ABC, and these two are the ground conductor. So, I say that U dash and W dash are ground conductor. So, if I do write down the impedance relationships with the currents for these 5 conductors, so I can write down that VA, VB, VC, then VU that is equal to 0, VW that is also is equal to 0, and that this is equal to say ZA, ZAB, ZAC, ZAU, ZW, ZBA, ZBB, ZBC, ZBU, ZBW, ZCA, ZCB, ZCC, ZCU, ZCW, and then ZUA, ZUB, ZUC, ZUU, ZUW, and then ZWA, ZWB to say again, please note that these are not primitive impedances. We have actually to arrive this, we have to first start with the primitive impedances, also by simultaneously considering the D dash conductor, and then we have to say, and then we have to utilize the condition that ID is equal to minus IA plus IB plus IC plus IU plus IW, and then we have to substitute that, and then after that we have to eliminate this equation VD, and then after that we will get this. So, this is the standard process whatever we have been followed for many cases. So, essentially we have actually skipped the first step. So, this is essentially the outcome after the first step. So, here again the idea is again identically the same. So again we also have to do the partition. So we do the partition like this. So now the partition is simple like this. So this is now the partition, and this is now the partition. So we define the vectors, and again as usual we say that this partition is ZA. This is a 3 cross 3 matrix. Z partition is ZB. This is a 3 cross 2 matrix. This partition is ZC. This is a 2 cross 3 matrix, and this is partition is ZD. This is a 2 cross 2 matrix, and we define as usual 3 vectors VA, VB, VC, then IABC is equal to IA, IB, IC, and we define IUW vector as IU, IW. We also define VUW vector, that is equal to VU, VW, but all these are 0. So then therefore it is 0, 0. So I call it a big 0 matrix, or rather it is a big 0 vector. So then therefore as usual VABC, VABC is equal to Z A into IABC plus ZB into IUW, and next equation is a big 0 vector, that is a 2 cross 1 vector, that is ZC into IABC plus ZD into IUW vector. So from here I can say that IUW would be minus ZD inverse ZC IABC. So now I substitute this. So then therefore we are process essentially it is called the Cron reduction technique. This is called Cron reduction. Then minus ZB ZD inverse ZC into IABC. So ZA ZB to IABC. So ZABC into IABC. So this technique where we are eliminating the currents, and because my voltages are 0 and all that, so this particular technique has a very specific name. This is called Cron reduction technique. Cron reduction. This is called Cron reduction technique, and this is a very powerful technique, and this is a very easy but very powerful and very widely used technique. So of course ZABC is ZA. So that is how we will take care of any number of ground conductors. So basically it is the case of partitioning the matrix. Now we are not going to derive it because now it has become pretty repetitive. Now we can now because we have handled so many cases, now probably we can also handle the case where I do have, say, bundle conductor. So bundle conductor, so these are bundle conductors, phase A, phase B, phase C, and then again it is a ground conductor. So it is A dash, and say this is R dash, this is B dash, this is S dash, this is C dash, T dash, say W dash. Suppose this is the case. So then now there are 7 conductors. So we will first write down the 7 conductors equation by using a 7 cross 7 matrix. And then what we will do, we will then take the current of phase A as IA plus IR, phase B current as IB plus IS, phase C current as IC plus IT, and this current is IW. So then therefore the finally the equations would be something like this, that VA, VB, VC, then basically VR minus VA, that is equal to 0, then Vs minus Vb is equal to 0, then Vt minus Vc is equal to 0, and Vw is equal to 0. So this is 7 cross 1 vector, and this would be one 7 cross 7 matrix, and then the currents would be here I A dash, I B dash, I C dash, and then I R S T and I W. And then this is a 7 cross 7 matrix. So we will partition it. So we will again partition it. Please note, so then this partition would be 3 cross 3, and then this, so we will do the partition here, and then it would be 4 cross 3, it is 3 cross 4, it is 4 cross 4. After we partition this, same. So then therefore by combining the techniques of considering the bundle conductor or the considering the case of an 1 or 2 ground conductors, we can now analyze any case for any number of conductor and they are connected in any fashion. And of course here we have considered only one and of course here we have considered only the case of 2 bundle conductors per phase. We can also extend this case very easily if there are more than 2 conductors per phase. So these are the basic fundamental techniques. Using these techniques we are able to calculate the impedance matrix of any line. So essentially the idea is that for any 3-phase unbalanced transmission line, finally after all this calculation, whatever is their distance among the phases, whatever is the number of conductors in the line per phase, irrespective of the number of ground conductors in the line, ultimately we reduce everything in terms of this relation VABC is equal to ZABC into IABC. So that we can do, and that we have looked into for last 9-10 lectures. So then therefore for any transmission line I can possibly model it by like this. Please note that this VABC is nothing but the voltage across the line. So it is the voltage drop across the line. So if there is a line between IABC, So if there is a, so this is phase A, phase B, phase C, phase A, phase B, phase C, and these lines can also be transposed, untransposed, or completely transposed. Let's say these lines also can be, let's say, partially transposed. Anything is possible, right? Ultimately, we can represent the line as a 3 cross 3 matrix, ZABC matrix. So, we can represent any line for the purpose of model as a, we can represent a line by its equivalent 3 cross 3 impedance matrix. As I mean, basically the similar concept is that for any balanced transmission line, we do represent a line by Z is equal to R plus Jx, right, between bus I and bus J. So, this is also bus I. So, this is bus I and this is bus J, this is bus J. So, if there is a 3 phase unbalanced transmission line having any kind of configuration between bus I and bus J, that can be represented by a 3 cross 3 impedance matrix. Whereas, in the case of a balanced transmission line, we do represent it by a single impedance. And please note that this impedance matrix, ZABC matrix, is a complex impedance matrix. All the values are complex number, essentially. Even basically the off diagonal elements are also complex number because of the presence of the earth conductor, or rather the earth resistance. So, with this we stop the modeling of an unbalanced power network for its series impedance. So, now we shall proceed to the calculation of the capacitance of the transmission lines. So, our next topic of discussion is capacitance of a transmission line. So, we will now start the topic on calculation of capacitance. So, this topic also we will spend some time on this because there are also different configurations. Some configurations we will consider, and then we will see by using those same basic fundamental technique we can calculate the capacitances for any configuration of a transmission line. Now, to calculate the capacitance, we have to recall one fundamental result from our basic electromagnetic field theory, which says that if I have a conductor at some point, so this is a conductor, say it is going inside the ground, or rather inside the page. So, and if this conductor has got the Qx, Qx is the linear current density of this conductor, and then if I have got a point, 2 points, any 2 points, point 1 and point 2, and so this is point 1, this is point 2, and then so then obviously due to the presence of this linear charge density, because of the presence of this charge, there will be some potential difference between point 1 and point 2, and that potential difference V12, so it is, this is basically nothing but potential difference between point 1 and point 2 due to the presence of this linear charge density. So, this is given by Qx by 2 pi E, E is the epsilon, basically the permittivity of the medium, log dx2 by dx1. So, what is these quantities? Qx, we have already said that the linear charge density, linear charge density that we have already said. Dx2 is the distance between dx2 is the distance from the charge to point 2. So this is dx2. So dx2 is the distance between point 2 and the charge, and dx1 is the distance between point 1 and the charge. So this is distance. So d stands for distance. So dxx, dxk, I can say that the distance of point k from the charge, where k is equal to 1, 2. So this relation is the fundamental relation, and we are going to use this relation. We are of course not going to derive this relation, because this relation we have already studied in our fundamental electromagnetic field theory. Now let us see that how do I apply this concept for calculating the voltage distribution in any system. So have what we have to consider is that suppose I do have a set of charges A, B, C, and say N. So this is conductor A, or rather charge A, charge B, charge C, charge N. Of course, these are conductors and they are carrying current, so that means they are carrying charge. So these are essentially conductors. So all of them have got some linear charge density. So QA, and so then therefore this conductor A has got a linear charge density QA. This conductor has got a linear charge density QB. This has got QC. This has got Qn. And then we also have the presence of ground. Then that there is of course a presence of ground. So there is a ground. And we know from again our basic electromagnetic field theory concepts that this presence of this ground, which is essentially considered to be a hugely conducting surface, the effect of this hugely conducting surface on these conductors can be represented by an equivalent image charges, where the image charges of all these conductors are located at the reflected point. So for example, if I have got this charge A, so its image charge would be here. So if this distance, it is the image charge would be here. So this is the image charge A dash. For this is the image charge B dash. Image charge means that its current density would be just the negative of the current density. It has got a current density of just the negative of this current density. This we know from the fundamental theory. Let me draw this again, otherwise we will use this diagram later on. So let me draw this again in a little better way, so that we can use this diagram in the next lecture as well. We don't have to spend time on this. Let me try to draw a better figure. Let me try. Okay. So what I have is some charge and say, and I have got the ground is here. So this is the ground. and this is conductor A, conductor B, conductor C, and conductor N. So, N can be any number, and this conductor has got the current density, linear charge density QA, this has got QB, this has got QC, this has got QN. And then if we are considering the image charges would be here. So, what we do is that image, basically the current density of the image charge would be equal and opposite of the original current density. So, then therefore, if for conductor A the current density is QA, for the image charge would be minus QA, and the location of this image charge would be just the location obtained by reflecting this charge with respect to the ground conductor, or rather with respect to the ground. So, then therefore, the location of this would be, say this is A dash, so this is minus QA. So, this distance is equal to this distance, because this is just the reflection. So, we can consider that this point A is basically, or rather we can consider that this point A dash is nothing but the reflection of point A with respect to the ground. Similarly, for charge B, we have got this. So, it is B dash, it has got minus QB. For charge C, it is somewhere here, and this distance will be equal to this distance. So, it is C dash and it is minus QC, and then of course dot dot dot, and then for this it is N dash, it is minus Q. So, I can say that A, B, C, N are the original charges, and A dash, B dash, C dash, N dash are the image charges. Image charges, and their location is nothing but obtained by reflecting the. Now, we also define some distances. Now, of course, if I have to find out, so now suppose that if I have to, uh, so now if I have some point A and 1 and 2, say this is point 1 and this is point 2. So, then therefore, the potential difference across these 2 points, point 1, 2, would be contributed by this charge, this charge, this charge, this charge, as well as all these image charges, that is this charge, this charge, this charge, this charge. So, then therefore, I can say, for example, V12 would be, for example, V12 would be, say 1 by 2 pi e epsilon, then say log dA2, sorry, QA, dA2 by dA1 plus QB log dB2 by dB1 plus dot 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 Qn log dN2 by dN1. So, these are the expressions of the voltages due to these individual A, B, C and charges, and then I have to also add the expressions for this, and then minus QA log dA dash 2 by dA dash 1, then minus QB log dB dash 2 by dB dash 1, and then dot 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 minus Qn log d n dash 2 by d n dash 1, right? So minus this. So from here, this is not there. So essentially from here, then we are coming. So this equation is continuing from here, right? So this is would be the total potential across point 1 and 2 due to the presence of all these charges. So QA, QB, Qn, and then minus QA. So this minus QA, so this minus due to this, then minus QB, then minus Qn, and these are the distances. So with this, we will be embarking on the calculation of the capacitances. So let's stop here, and then we will continue with this topic in the next lecture. Thank you.